some underdog team that won. Yeah. And then, like, people won a bunch of money. They had a 1 to 52,000 odds against them or something like that. 1 to 5,000. I think it was 52,000.
All right, everyone, welcome back.
And that one score to tie it, like the last minute. It's pretty impressive. That reminds me of the club that we were at 1 point times.
Can I start? Are y'all ready? Today's the last day, obviously, before our final, which our final is on Tuesday, I believe. Oh, Wednesday, sorry. Our final is on, wait, our final's on Wednesday? Yeah, okay, okay. Our final's on Wednesday. It's at 12:30. I know our class starts at 1. But the final is scheduled at 12:30. They do that for a reason. They offset things. You should not have a conflict with another class final unless you're at a different college somewhere. And we go till 3:15. Okay, on that final, I'm going to talk about the final at the end. I have a guide for you. Okay. So what I'd like to do today is I'd like to start by looking at what I handed you, which, does everyone have a copy of that? Missing one? Are there any extras? For some reason, I said for the copier to print out 25, and I don't think 25 came out. Oh, that's why. Oh, well, the printer messed up, or I messed up. I don't have one. That's it. Yeah, they printed. I got enough copies. They're just printed double-sided. So here's the deal. This is just directly out of the book, almost word for word out of 13.9. It's the theorem in that book, or on the page in 13.9. And I have it. I'll post it up here. I have it right here. So let's see. It's the almighty divergence theorem. It's also known as the Gauss's theorem. And here's what it says. Let E be a simple solid and S be its boundary surface. So we have some three-dimensional solid, okay, sitting here in space, right? Three-dimensional space. We've got some solid here. We're going to call this E. And let S be its boundary surface. So S encloses this entire solid, all right? Let S have positive orientation, meaning that the normal vectors on S, so S is the surface, right? Let the normal vectors be pointing out away from the solid, right? Let F be a vector field. So F is some vector field, P, Q, R, whose component functions, that means the P function, the Q function, the R function, have continuous partial derivatives on an open region that contains E, which basically means that within E, okay, within this solid, those derivatives have to be well behaved. Okay, continuous, meaning when you take derivative, you don't have any problems. No division by zero, no domain issues, okay? As long as that's the case, then if you're trying to find the flux, right? The flux is defined to be the surface integral over the vector field with respect to S, right? That's flux from 13.7, okay? That's flux. That this flux integral converts over to a triple integral over the solid instead of the surface of the div of the field with respect to volume, which is outstanding. In a lot of cases, this theorem makes life a lot easier. All right? You ready to see it in action? Today, I'm not actually going to post homework solutions for this because everything I'm going to do like 4 or 5 examples in class, and that's really like your homework guide, all right? So I'm going to go back. I thought it would be interesting to look at a problem we did in 13.7. Do you remember that? I believe we did that at the beginning of class last time. Does that look familiar? And we were asked to find the flux of this, right? And I timed it. I went back and looked at the video. It took me 17 minutes to do this problem in class. It took me 17 minutes. I'd like to try and do it with this new theorem, if I can. So do we have a solid that is enclosed by some surface S? Yes, we do, right? You can see the solid inside of this. Remember, this is the x-axis, the y-axis, z-axis. So we've got this picture. It's this bowl, right? And we've got the y-axis punching out of it, right? Back here, the x-axis comes out, and z's up here, right? Yes? And this whole thing, this solid E, we have the normals of the surface pointing away from it. And if you go back and look at the work that we did in class last time, that's the way we oriented the surface. And we had to go through and break it up into 2 surfaces and then do surface integrals. All right? But this looks like we can do the theorem. We have a solid. It's enclosed by the surface. Normals are pointed outward. We just got to make sure that the derivatives, right, the derivatives of our vector field are nice. So let's just look at what the div of f would be, because the divergence theorem tells us we're going to need to take a triple integral of the div. What is the div of f? So do you remember how to do div? You do the partial of the first component function with respect to x plus the partial of the second component with respect to y plus the partial of the third component with respect to z, right? And you add them all up. So I would get, what, 0 plus partial of y with respect to y would be 1, plus the partial of z, negative z with respect to z would be -1, and this would be 0. Oh my gosh. Okay, so that means that the surface integral, the flux, right? The flux, according to the divergence theorem, is the triple integral over E of the div of f, which is 0 with respect to volume, and that is 0. And that took me 17 minutes last time, and it just took me about, I don't know, a minute. Yes? That's a great question, all right? The question was, on the final, am I going to tell you which way to do it? Here's what I'm going to do. On the flux problem, I'm going to do a flux over a surface that does not enclose a solid, so you can't use the div. You can't use a divergence theorem, all right? But once you get to a surface, if I ask you to find the flux over a surface that is enclosing a solid, then I would be thinking this, all right? Now, when we did it, we got, like on one surface, I think we got negative pi, and the other surface we got pi, and then they canceled out, we got 0. So it matches up with what we did. It's nice, right? Okay. Done. Now, there was another problem that I did for your homework. Has anyone done the homework for 13.7? Yeah, of course, yes. Of course you have. Okay, that's the homework for this section, but there was a homework problem where you were given, this is from 13.7, number 29 in the homework that I assigned. What they did is they gave you this cube, and the cube was, it had vertices plus or minus 1, plus or minus 1, plus or minus 1. It was a cube. So it's basically centered at the origin, and there were all the corners of the cube Landed at every combination of those. So you had something like this. Okay, something like that. I don't know if that makes sense. This is popping out of the center of this side. This is popping out of the center of this side, and this one's popping out of the center of the top. Who watched my video? No? Oh man, y'all are breaking my heart over here. All right, because I had some trouble drawing it in my video. Okay, so there's this. This is you were asked in that problem to find the flux, and you were given x, 2y, 3z, and you were asked to find this, okay? And I did it, and what do you think I did when I did the homework for this? I split it up into 1, 2, 3, 4, 6 different surfaces. And then, which formula did I use? Do you think I used a shortcut, or do you think I used the super shortcut that had the normals in it? The super shortcut with the normals, right? Because all of these are flat surfaces. All the normals are nice. So I used that one, and I got through it, and it took me 14 minutes to do it on video. All right? Let's see what happens here now. Does this surface S enclose a solid? Yes? That solid in there is E. So I can convert this over to a triple integral over E. So this is going to become the triple integral over E of the div of F with respect to volume. Now I need to compute the div of F. So what is the div of F here? Do it right here. The div of F is 1 plus derivative of that with respect to y, 2 plus derivative with respect to z is 6, right? This is 6. All right, that's nice. So I'm just going to do the triple integral over E of 6 dV, right? And I can pull the 6 out, and that becomes triple integral over E of, 6. Triple integral over E of 1 dV. And that just means the volume of E. And what's the volume of this cube? Be a little careful here. This point right here was 1, 1, 1, right? 1, 1, 1. This one down here was 1, 1, negative 1. So the distance between these two is actually 2, not 1. Right? So the side of each side of this cube has a length of 2. Understand? So the volume of this cube is 8. So it's just going to be, where am I? 6 times 8, which is 48. And that's exactly what I got on my video. Isn't that better than breaking it into 6 surfaces? All right, but here's the thing. Divergence theorem is awesome, okay? I'm not going to downplay it. It's a great theorem. But you have to have a surface enclosing a solid. If you don't have that, you throw it out. It's kind of like, you remember when we had line integrals, where we were trying to compute the work on a line integral? We had the fundamental theorem of line integrals. If we didn't have a potential function, then we were just stuck with computing it. But if this curve actually went and came back upon itself, then we had Green's theorem. Because it came back upon itself, we could use Green's theorem. This is kind of the same thing. If you have a surface just floating out there and you want flux, you can't use this theorem. If the surface comes around and closes off on itself and encloses a solid, then you have the theorem. Okay? Do another one. This one won't be as clean, but it will still be better than the way we did it before. So I'm going to bring up, again from last class, after that problem, we did that one. That one look familiar to you? And we broke this one into 4 surfaces. It was the front side, it was the back side, it was the bottom, and it was this top piece, right? And I'll remind you what each of these were. I'll just put them up here. This front surface was x is 2. That's not a 2. That's a 0. X is 2. This back side was x was 0. The bottom of this thing was z was 0. And then this came from z equals square root of 1 minus y squared, where y was between -1 and 1. So you can go back and look. We talked about this last time. All right, so I'm trying to find the flux. I want to know this, right? So am I allowed to use the divergence theorem? Yes, because this surface S is all of those surfaces together and closes a solid, right? And so I'm going to need to compute the div. So let me get the div. This is going to be equal to the triple integral over E of the div of f dv, but the div of f, not as clean as the other ones we've had, right? What is it? 2x plus 2y plus 2z, right? Okay, well, it's not a constant, but it is what it is, right? So now this becomes the triple integral over E of 2x plus 2y plus 2z dv. And now we're back in chapter 12. It's just a triple integral, right? And you just need to come up with some way of controlling x, y, and z so that you can draw that region for me, that solid. So does anyone have an idea of how you could do that? Go to cylindrical coordinates or polar coordinates, right? Now what I'd like to do is I'd like to project this image onto the YZ plane, okay? Just so you can have an idea of what it looks like in the YZ plane. It's going to be the top half of this circle, right? That's a projection on the YZ plane. So I should be able to look at the Y and Z and look at this region as in cylindrical or in polar, right? The only other thing for me to figure out is what about x? Well, x is what? 0 to 2, right? So that should be easy to control, x between 0 and 2, and I'm done. It's just a matter of converting this region over because it's not a type 1 or a type 2. It's more of a polar region. So you all with me? So I'm going to go ahead and make my conversions now. I'm going to let y be equal to something and z be equal to something. What am I going to let them equal?
Y is going to be
R cosine theta, and this is sine theta, right? And then we have the Pythagorean identity, you know, y squared plus z squared is r squared. All those things are in play, right? And I'm going to put my restrictions. What are my restrictions on theta? What are my restrictions on r? And what are my restrictions on x? Because those take care of the three variables, right? So theta is between 0 and pi, because I don't want to draw the whole circle. I just want to draw the top half. And r is between, it was 1 if you go back and look at last class. This was 1 and that was -1, so r is between 0 and 1. And then x is between backside and front side 0 and 2. You all okay with that? All right. So I'm just going to rewrite this triple integral. I'm going to rewrite it with those variables. So it's going to become triple integral. I'm going to put my limits of integration on here in just a second. 2 times x is just, well, can I pull a 2 out of everything? Okay, 2. X by itself is, well, it's one of our variables, so just x. The y by itself, what was y? R cosine theta. And then plus, what was z? R sine theta. All times r, because we did do a conversion, right? Cylindrical is polar, so I have to put an r. And then I have, what, d theta, dr, dx. I can go in any order I want. I'm just going to go dr, d theta, dx. And then I'll put my limits. I'll start from the outside in. X's go from 0 to 2. Theta goes from 0 to pi. And R goes from 0 to 1. Good? I'm going to take this all the way. This is equal to 2 times the triple integral 0 to 2, 0 to pi, 0 to 1 of xr plus r squared cosine theta plus r squared sine theta dr d theta dx. So I just distributed the r through. And now I'm going to integrate everything with respect to r. I don't think I need this picture anymore. I need the space, though. Equal to 2 integral 0 to 2 integral 0 to pi. Okay, antiderivative of this with respect to r is 1/2 xr squared. Yeah? Antiderivative here, 1/3 r cubed cosine theta plus the same thing, 1/3 r cubed sine theta. Evaluating r equals 0 to r equals 1. And I still have out here d theta dx, right? When we plug in 1 for r, we're going to get some stuff. When we plug in 0 for r, everything goes away. So we should just be at this. 2 integral 0 to 2 integral 0 to pi. What do I get when I plug in? 1? 1/2 x plus 1/3 cosine theta plus 1/3 sine theta d theta dx. Integrate with respect to theta now. Equals 2 integral, oh, I'm integrating only 1 now. 0 to 2, antiderivative of 1/2 x with respect to theta. 1/2 x theta, right? Plus 1/3 sine theta minus 1/3 cosine theta. Evaluated theta equals 0 to pi dx. Almost there. Be a little careful here. 2 integral 0 to 2. All right, let's plug in pi first, right? For theta, we get 1/2 x times pi. All right. Sine of pi, 0. Cosine of pi, -1 times -1/3, so plus 1/3. Agreed? When you plug in 0, be careful because not everything goes away. Theta goes 0 here, that's gone. Sine of 0, that's gone. Cosine of 0 is 1, but then minus 1/3, but we're subtracting this one, right? So minus 1/3. So it's going to be plus 1/3, isn't it? So here's where we are. 2 integral 0 to 2 of 1/2. I'm going to write pi x instead of x pi plus 2/3 dx. And integrate with respect to x. 2, antiderivative here. 1/4 pi x squared plus 2/3 x evaluated 0 to 2. When I plug in 0, it's all gone, right? When I plug in 2, let's see what I get. 2, let's see, 2 squared 4, but then 1/4, so just pi, and then plus, plug in 2 here, 4/3, but then times 2. Oh, wait, sorry, I haven't done that yet. 4/3 like that. And then you can distribute the 2 through 2 pi plus 8/3, which is the same answer you would have got had you done it the other way. But this required a little work. It took me 20 minutes to do it the other way. I think that might have been a little faster. I don't know. Took 10? Okay. So a little more efficient, all right? Questions? So the things that you're going to be looking at when it comes to divergence theorems, first of all, can you use it, right? Like, do you even have the right thing to use it? Then, take a look at the div. Is the div nice? Is it something you really want to mess with? And then look at the solid itself. Can you find appropriate restrictions for your triple integral? If those all look like they lend themselves more to the theorem, then use the theorem. If not, then just do it the traditional way, break it up into separate surfaces, and be done. All right, I have another one. I'm actually moving a lot faster than I thought I was going to go here. We may have time to play, what's that game? Heads down, thumbs up. We'll turn down the lights. Everyone puts their head down, put your thumb up, and then we go over. Yeah? You want to do that? We haven't played that in a long time, huh? What is it, what?
Heads up, 7 up.
Yeah, heads up, 7 up. I knew it had something to do with 7 up. We'll do that at the end, okay? All right, this, just so you know, this is from 12.9. This is out of the homework. This is number 6. Actually, I did assign this for homework, but I'm going to do number 6. So here's what it says. Here's a vector field, x squared yz, x y squared z, x y z squared. All right, that's your vector field. It's giving you a surface S, which is a box that is the intersection of these planes. Box, which is the intersection of, or I should say this box, not the intersection, is bounded by these planes. The intersection of those would not work. It's bounded by x equals 0, x equals a, y equals 0, y equals b, z equals 0, z equals c. Find the flux. Find the flux through this surface. X equals 0 is the YZ plane. Y equals 0 is the XZ plane. Z equals 0 is the XY plane, right? So you're basically in the first octant. And then X equals A is just a plane that is parallel to the YZ plane. And let's assume A, B, and C are positive here, okay? Just for simplicity's sake, so when I draw it, I should have something like this. Here's the first octant. Here's X, here's Y, here's Z. If X is A, Y is B, and Z is C, then I should get a box that looks like this. Do y'all agree with that? Sorry, it's not, I should say rectangular box, right? Rectangular box. It's not a cube. Does that make sense to you? X equals 0 is the back side of this. X equals A is the front side. Y equals 0 is the left side. Y equals B is the right side. Z equals 0 is the bottom. Z equals C is the top. All right, that's our surface, and we want to find the flux. Automatically, we're thinking this is better off as a divergence problem, right? Because that is very simple to figure out what the restrictions on X, Y, and Z are, right? But the div is what we still need to figure out whether or not we want to mess with. So what is the div of F here? So derivative of that with respect to x is 2x yz plus another one of those, right? 2xyz plus 2xyz, which is 6xyz. That seems like something I don't mind integrating. So this should turn into the triple integral over e of 6xyz, so I'm pulling the 6 out, with respect to volume. So we need to be able to come up with our constraints on x, y, and z that will create that solid E, right? And I don't need to convert to polar or cylindrical, right? This is all straight up, this is rectangle. So what are the restrictions on x, y, and z? 0 to a, 0 to b, 0 to c. And so my triple integral over here turns into, I'll go 0 to c, 0 to b, 0 to a of x, y, z, d, x, d, y, d, z. I could do that. I could have done that in any order, right? Since these are all separated by multiplication, can I break this into 3 integrals and multiply them together? Yes, or I could just do it all at one time. I'm going to break it apart. I'm going to have 6 times the integral from 0 to c, and that goes on the z variable, right? Z dz times integral from 0 to b of y dy times integral from 0 to a of x dx. And the 6 does not, you don't get 6s on each one of those, right? It's just 6 one time. Understand what I did? All right, I think if we do one of these integrals, we can see what all of them are going to turn into, right? So what's the antiderivative of z dz? Well, it's 1/2 z squared evaluated 0 to c. So you get 1/2 c squared. That's what I'm going to get for that one. This one should turn out to be 1/2 b squared, and that one should turn out to be 1/2 a squared. And then times 6. So I'm going to have 6 times 1/2 z, not c, c squared, times 1/2 b squared, times 1/2 c squared, which is 3/4 a squared, b squared, c squared. I put it in alphabetical order. That's it. Understand? Any questions? Yes, this last one, thank you, should be an A. Appreciate that. Because my last integral is with respect to x, so that should have been a squared. No questions? Nice theorem, huh? I've got another, let's see, how many more do I have here? One, I have one, two more, and then I'm going to show you one last thing, and then we're going to be done, and you can start crying. My 6-year-old daughter broke my heart this morning. Mom had put her hair up in a certain, like, almost like, what's the Star Wars lady that has the little, almost like Princess Leia buns. They didn't look that ridiculous, but little things like that. And she did that last night. My wife leaves real early to work, so I usually get my daughter up, take her to school. And one of them was messed up, so I tried to fix it. And I took it out of the thing that was holding it, and I could not get it back, and she cried for the rest of the morning about her hair not, I couldn't do anything about it, I don't know what to tell her. And today was supposed to be picture day. That's why she was so upset. But it turns out that it's next week, so she got to school and she's really emotional, and when she cries, she's real light complected, and when she cries, she gets real red and puffy in her face, and so she was even more upset that she was upset because she knew she was going to look like all puffy in her picture. So I hope when she got to school and they told her no pictures today that she was finally relieved, but I felt bad.
It's okay, life is full of disappointment.
That's right. I'm trying to get her to understand it's not all candy and fun.
She rocked the one button.
What's that?
She rocked the one button.
My neighbor, we switch off taking them to school, and my neighbor, she tried to salvage what she could. It was better than I did. Okay, so here we go. We have a field here. We're asked to find the flux, over this surface. Why am I telling you that story? Oh, because I was saying you can cry. I was like, class, we'll be done. You can cry, and I was thinking about my daughter crying. Okay. Like, what the hell am I telling you that for? Okay, the solid we have here.
Random story time.
Yeah, the surface we have, S, comes from this picture here. All right, we have x is equal to 2, backside x is equal to -1, and this cylinder is y squared plus z squared equals 1. Do y'all kind of see it? I don't really like my x, y, z axes there, but is that okay? All right. So the surface is the entire surface that encloses, so both end caps and then the cylinder around it. So what do you think? Divergence theorem? Yeah, of course. So let's look at the div first. What's div f? 3y, not a vector. 3y squared plus 0 plus 3z squared, right? What's that? Yes? What happened? Did you just upset everyone? Everyone's like, okay, one by one, they're just leaving that table. I don't know what you guys are doing over here, but all right, this is it. This is our div.
Yep.
All right, I think we're okay integrating that. And you know what makes me feel even better about it? The y squared plus z squared, when I factor a 3 out, is going to lend itself very nicely to the polar conversion or cylindrical coordinates I'm going to go to describe this surface, because I have circles in the yz plane. So everything's looking like perfect here, all right, for what I want to do. So this is equal to triple over E div f. I'm going to pull the 3 out of y squared plus z squared dv. All right, tell me what my conversions are. What are my conversions here? Okay, y equals r cosine theta. Z is r sine theta. And then everything that follows from that, right? The restrictions I will place on theta are what? 0 to 2 pi. So remember, if we're picturing this cylinder, where it intersects the YZ plane creates a circle of radius 1, right? Because of this equation. And so I want the whole circle, 0 to 2 pi. I want my radius to go between 0 and 1. And the last variable, which we need a restriction on, x is between -1 and 2. So now this becomes 3 triple This is actually r squared because of the Pythagorean times r because we did a conversion. So it's really what? R cubed? R cubed. D, does it matter? Order here? No. So r theta x, okay with you? X goes negative 1 to 1, or 2, sorry. Theta goes 0 to pi. R goes 0 to 1. Dot, dot, dot. Do you want me to dot, dot, dot that? Yes? Okay, 9 pi over 2 is what you will get. Okay, the last one is the most thought-provoking as far as the examples that I'm going to do that relate to your homework. And this is based on number 13. All right, here it is. Here's what they say. F is defined to be the magnitude of R times R. R is the vector x, y, z. S is the hemisphere z equals square root of 1 minus x squared minus y squared, and the disk x squared plus y squared is less than or equal to 1. And they want you to find the flux. Let's try and draw S first and see if the div theorem, right, divergence theorem, will apply. This is the top half of a sphere, isn't it? Because if I square both sides, I get z squared. If I move all my variables to one side, I have the equation of a sphere. But because it's solved for z, it's only the top cap. So I know I've got the top cap of a sphere of radius what? 1. And then that's the top of it. And then the bottom is the disk that is the base of it, right? Pardon?
Do we have to add it?
What do you mean add it?
Like, because aren't they two close surfaces?
They are two separate surfaces which enclose a solid.
Okay.
Okay? I think the book also says that this is in the xy plane, which means that because if I don't say this is in the xy plane, this is actually a solid. It's like a cylinder, right? If that was equal 1, that'd be a cylinder. Less than or equal 1, this would be like a solid bar. But if I say it's in the xy plane, it's just the bottom. Understand? Any questions on what S is? We're all right? So E is the solid it encloses. We have that. We have an E in here. So I should be able to use the divergence theorem, but I'm going to need to come up with the div of F to do that. And we need to get a grasp on what F is, because F was not given to us in its standard form. So what is it? F is actually this vector. So this is like my PQR. Not yet, though. This is the like the vector field, but we're multiplying it times the length of the vector. That's what F is. So it's like a position vector, right? X, Y, Z is where you are, times how far away you are from the origin. So you're scaling it by how far away you are. That's the field. So I'm going to rewrite this in terms of X, Y, and Z. What is the magnitude of R by definition? Square root of x squared plus y squared plus z squared. That is just a number, isn't it? That's just a number? Okay? And then we have times the vector r, which is x, y, z, right? That's what that means. And since this is just a number or a scalar, I distribute it through to each component. So this becomes x root x squared plus y squared plus z squared, y times root x squared plus y squared plus z squared times z comma z times x squared plus y squared plus z squared. That's my vector field. It's ugly. I'm going to still go for this. I'm going to try and get its div. So I need to take some partial derivatives and add them all up, right? Let's talk just about this one for a second. What would the partial with respect to x of this be? Because that's what I'm supposed to do right now, right? You would have to use product rule, right? We have a product happening right here. And chain rule. So let's try it. What is the derivative of x with respect to x? 1 times this, right? So I'm going to start abbreviating this to make this easier, all right? This is going to be 1 times the root of all this stuff, junk. I'm going to call it j. I'm even going to get more lazy. More lazy? Lazier? More lazier. You know what I'm saying, right? Root of, I'm not even going to write the word junk. I'm just going to write j, okay? Plus what? What's the derivative of the square root of some, okay, x, you want me to put the x first? Okay, x, derivative of the root of something is 1 over 2 times the root of that stuff, right, the junk, times the derivative of what's inside of it with respect to x, which is just 2x, right? The 2's cancel? Y'all okay? So I get this. I get root junk plus x squared over root junk. That all right with you? I'm just going to leave it like that. I could get common denominator and all that, but is it all right if I leave it like that? Okay, now this is the partial with respect to x. The only difference between this and this is there's a y here, but I'm differentiating with respect to y, so everything should be exactly the same except y squared, and the last one should be everything the same except z squared, right? That'll be nice. So with that in mind, the div of f should be this root junk plus x squared over root junk plus root junk plus y squared over root junk plus root junk plus z squared over root junk. You can write junk. Yep, that's okay. Yeah. All right. What can I do here? I've got 3 things that are identical. Root, root, root. So 3 of those. So this is 3 roots of junk plus, and then the things that remain all have a root junk on the bottom, right? So I can combine them together into one fraction, and I'll have root junk on the bottom, x squared plus y squared plus z squared. But what is x squared plus y squared plus z squared? That is the junk. That is the junk, isn't it? Yeah? So I have 3 root junk plus junk over root junk. And what's junk over root junk? It's root junk, isn't it? So this is 3 root junk plus root junk, which is 4 root junk, which now I'll actually write in what it is. There it is. Okay, so any questions? I look at this and I say, crap, man, well, I really don't want to integrate this because, right, this is going to be our integrand. But look at our region, E. How can I represent that region? Spherical coordinates, right? That's perfectly suited for spherical coordinates, isn't it? And if I go to spherical coordinates, what is x squared plus y squared plus z squared? What is this? That's rho squared, but then square root. So that's just rho, isn't it? This is just 4 rho. That's all that is. With me? All right, hope so. So here's what I've got now. I've got my triple integral over E of div f dv. I'm going to switch to spherical here. Remember all our spherical conversions? It was like x was, I don't know, like rho cosine theta cosine phi. We used u and v also. And then y was like rho sine theta sine phi. This isn't right. Something's wrong. No? Phi. Phi or phi. You'll hear people say it both ways.
Because I said V and then they're like, oh, it's fine.
Who said that?
Some people.
I've said it both ways. You'll find people in the math community that say it both ways. Like they'll say it one way and they say, that's the way. And then you see someone else, no, it's the other way.
You know that honor society, they Phi Theta Kappa, and so I said that. And
Yeah.
they're like, oh, it's Phi Theta Kappa. Oh, good for you.
Yeah,
Whatever.
I know. Yeah, it's just one of those things, man. It's like Euler and Euler. You'll hear, there's a mathematician, Euler, Euler, you'll hear people say Euler. I believe Euler is correct, but I think phi and phi, you're okay either way.
Though they kind of raise a valid point, then is it Wi-Fi?
Wi-Fi? They asked Wi-Fi?
Yeah, is it Wi-Fi?
Why?
It's
All right. Yep. Rho sine phi phi. We'll call it phi phi instead. Okay? Yeah, that's why I was saying this wasn't right. Something wasn't right here. Okay, sine. Yeah, there we go. All right, that's our conversion. Now, if we're going to use this conversion, if we want to draw this solid, right, using spherical coordinates, give me the restrictions on those variables. Let's start with rho. We can start with any of them, but what did I do? For what? Did I write it down wrong? Jeez, what's going on here? Or you know what I was thinking of? I was thinking of what we have to include in our integrand. No excuses, except that it's the last day. All right, so there's our spherical. We don't actually need any of this right now, right? I mean, we just need to find restrictions, which means we need to know, back here in this hemisphere, rho was the radius. It was the distance from the origin out to my points. And if I want the whole solid, I want to go from 0 out to, well, this is a unit sphere? Yes, it is. How do I know it's a unit sphere? Square both sides. Move the variables over. You can see your radius there. Okay, so I know that rho has to go between 0 and 1. Theta. Theta is the angle that swings you around like this, right? 0, 2 pi. And phi phi is from the z down, right? So z down to the xy plane. I want that 0 to pi over 2. There we go. That should draw it. So we've got triple integral. I'll put my limits of integration in just a second. I need to do the div of f, which we turned out determining was this, right? X squared plus y squared plus z squared. we said was rho squared and then square root. So this is 4 rho. But every time that we do a spherical conversion, we must include rho squared sine phi phi. I like that. That just has a ring to it. Phi phi or phi phi? Phi phi? Phi phi? Faux fum? Everyone got this? This is the actual div f. This is what we have to put because we went to spherical. And finally, my variables. Doesn't matter what order, right? D rho, d theta, d phi phi. And you've got 0 to pi over 2, and 0 to 2 pi, and 0 to 1. Dot, dot, dot. Dot, dot, dot. Yeah, you could split this up because your rows are separated from your phi's, and so the answer here is 2 pi. Nice clean answer. All right. I like that one. So it's highly unlikely that you're going to see a problem directly out of the section for spherical coordinates if I can ask you a div problem that requires you to go to spherical coordinates, right? Your final is going to be one problem. And it's going to kill 32 birds with one problem. No, I'm just kidding. All right. Yeah. Okay, this is the last thing I'm going to show you this semester. This is going to be, well, probably take me about 20 minutes. We'll see. Maybe not. So I'm going to start off with just setting up some concepts we're going to need for the problem. This is not a problem that I would ask you on the test. This is more just kind of, this is kind of cool stuff that has to do with divergence theorem. So let's say that we have, I'm going to do a different color here. Let's say that we have a surface, three-dimensional surface, all right? So this has, it's three-dimensional. I'm just doing that so you can kind of see it has some depth to it, all right? I'm going to call this surface S2. And that surface S2 encloses a solid, doesn't it? I'm telling you it's closed, all right? All right. Now, inside of S2, inside of S2, I'm going to draw another solid, another surface, which again is a closed surface. And I'm going to call this one S1. It's inside though. Yeah, okay, yeah, jelly-filled donut. There you go. That works. Except there's no hole on the outside where this can start spewing out. But yes, same principle. Remember, you're talking to someone who spent a year talking about the difference between a coffee cup and a donut. So, all right, so you see the picture? Okay? Now, the normal vectors on S2 point outward, right? Like this, away from the solid. That's our standard orientation of the normal vectors of S2. I'm going to call these N sub 2 to stand for the normal vectors for this surface 2. The normal vectors for S1 in standard position would point away from the solid also, right? So the normal vectors for this one would point away, all right, like that, yes? And there's more on the other side, and they're pointing away from the solid. With me? So the vector, if I take this vector and I point it inward, right? Take this one and point it inward, That would be the opposite orientation, wouldn't it? And that vector that points in would be negative n1, wouldn't it? Okay. Understand the picture of what's happening here? Yeah. So I want you to consider right now E, a solid that is the solid between the two. That's the bread of the jelly-filled donut, right? That's the part I'm talking about. All right, consider that solid. And consider the surface that would enclose it. It actually would require two surfaces, right, to enclose that? But your normals need to point away from the solid. So does it make sense to you that I could write this? Just see if this makes sense. That the triple integral over E of the div of F, by the way, there's a vector field sitting here. F is here, PQR. I need a vector field or I can't talk about flux, right? Okay, so there's some vector field sitting here in the background the whole time. Do you agree that this should be equal to the surface integral over S of F ds, where S encloses E, right? So don't confuse S with S1 and S2. S is the surface that encloses the bread of the donut. Can we go with that? Good, I'm glad you mentioned that because I think it makes sense. So S is actually made up of two surfaces. One is S2, right? And the other one is S1. Now, is S2 oriented properly in terms of how it encloses E? Are the normals pointed away from the bread? Yes? So I could say that this is equal to the surface integral over S2 of F dot ds plus now the other surface, which is S1, right? Do the normals of S1 point away from the bread? No. So I need them to if I'm going to orient it properly, right? So instead of looking at S1 normals pointed towards the bread, I'm going to reverse them. So when I reverse the direction, it changes the sign of the integral from plus to negative. And now it's S1F dot ds. Does that make sense to you? Okay. If we have a solid that is between two surfaces, then that formula should hold, right? I'm going to erase all this and I'm going to start the problem. I just need this in a minute, all right? I want you to consider in three-dimensional space an electric charge, which I will call Q, capital Q, at the origin. Okay, so imagine that we just have something that has a charge to it. Positive, negative charge, it has a charge. And I'm going to say, here it is, and I'm going to call that the origin. All right? So I've got this picture, I've got something sitting here, and it has an electrical charge on it. All right? When you take a physics class, they will tell you, due to, how do you say this? Coulomb's law. will say that the electric force which we will call F of x, all right? The electric force is a field. So imagine that this is creating a field, all right? The electric force F of x, now x is a vector, so you plug a vector in to this field and you get an answer, and that's your force. The force of Q on another charge lowercase q at the point xyz, or if you'd like, you can look at that as a vector xyz, is equal to E Q, capital Q, over magnitude of x cubed times x. Anyone? Oh, I forgot the equal sign in here. I was hoping that someone had seen this before. Yes? Some version of it, or close? Look close?
Yeah.
Okay. Here, do they use epsilon? What do they usually tell you for that? Epsilon, okay. Epsilon is a constant, and that constant depends on the units that you want to measure in, okay? What I'm trying to do today with this example is show you a physics problem that there's a formula for something here in a second that I'm going to derive the formula, all right? So this is the electric force. But in physics, they're not interested in the electric force. They're interested in the force per unit charge. So what they do is they come in, they take this vector field. This is a vector field, isn't it? There's a vector in here. Okay. These are all numbers, aren't they? Number, Q is a charge. It's going to be a number. Capital Q is a charge. That's a number. This is the magnitude of a vector. That's a number. So this is all a number times a vector. So that's a vector. It's a vector field. If we define a new vector field, capital E of x, to be equal to that field divided by Q, then what would happen if I take this field and divide it by Q? Little q. Little q's cancel, right? And I just get E epsilon Q over x, magnitude of x, times the vector x. Okay? And this is your force per unit charge. Or, yeah, force per unit charge. I'll put it here. Force per unit charge. And this is something that will always hold for any charge that you put at the origin, and then you place another charge out here relative to it. This has a position, right? The position of this is x, y, z. Then the force per unit charge is some measurement of what's happening between these two, right? Got it? How these two charges are interacting with each other. All right, what do I want to do now? I want to get to the problem. This is the big thing we're going to work with right here. I want us to show that the flux of E with respect to S, okay, so this surface flux is equal to 4 pi epsilon times Q. Does that all look familiar? I don't know. Maybe you've seen that. Maybe. That this is equal to that for any S which encloses the origin. That's it. That's what we want to show. So if I put a charge here, if I put charge Q at the center here, have another charge here, then the force per unit charge along a surface, right? You have this surface. Imagine any three-dimensional surface, right? That encloses the origin. So it encloses our charge, right? That will always be this right here, which means it's always a constant, but it depends on the charge that you started with. Okay, so you change this charge, this is going to get bigger or smaller depending on Q. We want to show that holds for any surface that encloses the origin. Now, we ran into a problem like this a while back. I showed you this example where we were trying to show something for any circle or any curve that enclosed the origin. Do you all remember that? And we were able to do it. We were kind of sneaky about it, but we did it. I'm going to do something similar here. All right, so the first thing I'm going to do, here's my picture. I want us to call this surface right here, just to make it easy to go back and look at what we drew a second ago. Let's call this right here S2. All right? So this surface that encloses our origin point, this is S2. I would like for us to consider S1. So this is my solution. Consider the surface S1, which is going to be a sphere of radius A, which is inside S2. So do you agree that if somebody gives me a surface that encloses the origin but does not actually touch the origin, that I can always find a small enough sphere to fit inside of S2? You agree with that? You have to agree with that. Yeah. You're okay with it? Okay. So this inside of here, it might be really small, but I should be able to control I pick a radius which is going to make it small enough to fit inside. So here I go. Here's my sphere sitting inside. That's S1. You still with me? Yeah? All right. This looks a lot like the donut, right? That we did a second ago. What can you tell me in terms of what we did before? If E is the solid between them, be very careful there, solid between them. Please put it away. Okay. If the E is the solid between them, which is the bread part, right? Then what can we say? I wrote down a thing here a second ago. Yes, it's the triple integral over E of the div of F, right? dV. Our field here that I want to be working with is E, okay? Don't confuse these two E's. F was the force field, but I said let's define E to be the the force per unit charge. So do you agree that our new field out here is the field E, not to be confused with the solid inside, which is just E without a vector? Should I change the name of the solid, or are y'all okay? Okay. All right, so this should be equal to what? The surface integral over S2 of E dot ds. It's still with respect to surface area, so ds. Then what? Minus surface integral over S1 of E ds. We still good? Now, if you remember how I snuck in and did the other problem, I was able to show one of these was something real quickly and easily. I'm going to do something similar here. I'm actually going to work on the left side of this right now, which means I want to find the div of E. All right? What's going to happen is that this is actually going to become 0. And because it's 0, that means that these two, when I move this one to the other side, must be the same. And if these two are the same, that means to find this flux over S2 is equivalent to finding this flux over S1. And I can do that because I have a nice, good definition of what S1 is, right? But I still have to show that the div of E is 0. So that's what we get to do now. So I'm going to say here now, but the div of E equals, well, what is E? Div of, it's a vector, isn't it? Tell me what E was. It was epsilon q over magnitude of x cubed times x, right? That was it. But what is x? What is this x vector? Maybe we never stated that from the beginning. The x vector is the vector that goes from the origin to little q, which is just the point x, y, z, which is the vector x, y, z. So I want you to convert this now to say this. E, or epsilon times q over what is the magnitude? What is the magnitude of x? Square root of x squared plus y squared plus z squared, all of this cubed, right? Times x, y, z. Right? This is a constant. I multiply it through. So this becomes, I forgot to put my div in here. I haven't taken the div, have I?
No.
I'm taking the div of this. I'm taking the div of this. I'm going to do that as I work through here. So I need to do the div of, as a vector, it's x times this, right? So EQX over root x squared plus, it's about to be junk. Give me just a second. And then here, E epsilon q y over square root of x squared plus y squared plus z squared. And then epsilon q z over square root of x squared plus y squared plus z squared. I need the div of that. So maybe we can do what we did a second ago. We can just look at one of them and see the pattern in the derivative and just do the same for the rest? Okay, what is the partial with respect to x of epsilon qx over root x squared plus y squared plus z squared? All right, quotient rule. Derivative of the top with respect to x, epsilon q times the bottom. I'm going to go root junk, right? Root j. Minus the top, epsilon q x times the derivative of the bottom, which is 1 over root junk. Yeah, you're going faster. 1 over 2 root junk times the derivative of what's in there, 2x, and that's it for the top, right? All of this divided by root junk squared. So just junk. We still good? 2's cancel. See if. We did. Hold on. This is bad. This is bad. No, we didn't forget. I forgot. Yes. Yeah, do y'all see that? Look, when we distribute this cube, do y'all let me forget this? You did on purpose. Look, I'm going to rewrite this to the 3/2. Is that all right? 3/2. That's going to change some things here, isn't it? 3/2. We got to start this over. I think the top, this is the same, but it's not root junk, it's junk to the 3/2. This is the same. Yeah, I'll get to that. Let's do this part right here. Okay. We all right there? All right, well, derivative of this is 3/2 the junk to the power came down, so 1/2 times 2x. All over. This, when we square it, the root goes away, so you just get j cubed, junk cubed. It's a lot of junk. I'll try and clean that up over here. Everything has, well, do we want to clean it up or do we want to leave it? I mean, it's kind of up to you at this point. Can I just leave it?
Yeah.
I just leave it. So if I go to do the div, I'm going to have this expression, again, added to this with a y squared. These 2's will cancel. I'll get an x squared here. I'm going to have a y squared on the next one, and the last one I'll have a z squared, and that's the only difference between them, right? So my div f, my div e, is going to turn out to be epsilon q junk to the 3/2 over junk cubed. I'm splitting this up into 2 fractions, okay? Then I have minus epsilon q x squared junk to the 1/2 over junk cubed. Y'all seeing what I'm doing here? 3 epsilon. And then repeat that, right, 2 more times. So plus epsilon q junk to the 3/2 over junk cubed minus epsilon q 3 epsilon q y squared junk to the 1/2 over junk cubed. One more time. Epsilon q junk to the 3/2 over junk cubed minus 3 epsilon q z squared junk to the 1/2 over junk cubed. Those are all the same. So I have 3 of those, right? Okay, so I have 3 epsilon q junk to the 3/2 over junk cubed minus, now these all have a minus, right? All have a minus, so how can I write that? Minus 3 e q j to the 1/2 over j cubed. That's what they all have in common, right? This one, and this one. So I'm factoring that out of those 3, and what's left over here? I will in a second. I will. What's left here? The x squared plus y squared plus z squared, right? X squared plus y squared plus z squared. But what's x squared plus y squared plus z squared? No, you're at the last problem. That was junk, wasn't it? That was junk? That was the junk.
Aren't we gonna do spherical anyway?
No, we're not. This is going to be 0.
Oh, too bad.
3, yeah, too bad, right? 3 junk to the 3 halves over junk cubed minus 3 epsilon q junk to the half over junk cubed. But this right here you said was just junk, right? And then junk to the half times junk, add the exponents, you get junk to the 3 halves. And then they're identical. 0. Right? So div is 0, which means that the left side of that equation I wrote earlier is 0. Okay. Not done yet. Therefore, triple integral over E of div E dv being equal to the surface integral over S2 of E dot ds minus surface integral over S1 of E dot ds is actually 0 equals this, right? Which means that they're equal. Are we done? What do I have to do? I actually have to figure out one of these, right? This is the one I'm interested in, right? This is the one that I want to know. This is the one that I created to make this problem work. The S1 was that sphere with radius A. Yeah? Okay, so I'm now going to go after this one right here. I'm going to see if I can do this surface integral. All right? Now watch how I'm going to do this. We could come up with some parameterization of the sphere and all that stuff, but I'm going to do something even more clever, I guess. I'm going to try and use this one right here. I'm going to try and use this formula. Because I think I know something about the normal vectors on a sphere. If you give me a sphere, and here's the origin, if you pick any point out there, of course that point has the coordinates x, y, z, but the vector that goes there from the origin to that point is parallel to the normal vector at that point, isn't it? It points in the same direction. It just doesn't have a unit length. Right? So if I wanted to come up with the normal vector, which would be sticking out of here like that with unit length, I would take this vector and divide it by its own length, right? Right? That's what I would do. All right, so I'm going to write this up here. This is equal to this. What is E? We wrote that, we had that down a second ago. By the way, this is D. Sorry. In the formula, because I went from S, right? Since I did the normal in there, this becomes D. D is the domain of the parameters that draw S. What was E? Epsilon Q over magnitude of x cubed times the vector x, right? That was E. I want to dot that with this right here, right? And look at this. Isn't this just x over magnitude of x? Isn't that what that is? Dot that with x over magnitude of x ds. what is a vector dotted with itself?
It's magnitude squared.
It's magnitude squared. Go back, this is chapter 10, way back in the day. All right, this is double integral over d of EQ of what? Magnitude of x cubed times these two together is magnitude of x squared over this is magnitude of x, then ds, and what is that? Because there's 4 of them down here, 2 of them up there, cancel out, get this? All right, all of this said, what can you tell me about the magnitude of any vector on this sphere? Close, not 1. I chose the sphere. It's A, right? Isn't the magnitude of, remember how we chose this guy, S1? Well, I erased S1 a long time ago, but, right? This was a sphere of radius A. So if I take any point on that sphere, it has a distance of magnitude of A. So I can replace this down here with A squared. So here's where I am now. This is equal to double integral over d of EQ over A squared ds. And if you recognize now, let me check something here. No, we're good. I mean, we're good. Isn't everything here constant? Which is the surface area of my surface, which is the surface area of this sphere. The surface area of a sphere is 4 pi r squared, right? 4 pi r squared. This has a radius of A. What's the question? Or no? You good? Would you agree that this has an area of 4 pi a squared because the way I chose it? So this becomes EQ a squared times 4 pi a squared. Cancel, and you get 4 pi epsilon q, which is what we wanted to show. Check. Yes. So I think a lot of times in like a physics class, what will happen is they'll give you a formula, and you just know that they just tell you, like, that's it, right? Like if you ever are trying to find the charge, the force per unit charge, if your surface encloses the origin, it's a closed surface, then you just need to know what the charge at the center was. Take that, multiply it times the constant, which has to do with the units you're in, multiply by 4 pi, you're done. This was to show you where that formula comes from, and they all come from something, right? All these formulas come from some mathematics, and I wanted to illustrate how the divergence theorem is used to generate a formula like that. Okay, I have one more handout. This is your guide to the final. Even if you have one, just pass these around. All right, so can we talk about this? I have 5 minutes. That took me a lot longer than I thought it was going to take me. I'm just going to start by saying that I really do appreciate that a strong majority of you really did put a lot of time and effort into these take-home exams. You know, when I started this class off in the very beginning of the semester, I told you, you know, these take-home exams are going to require that you put a lot of effort into them. So I do appreciate all the time that you put into it. I hope that you learned a little bit about yourself and your abilities and just that it was a good experience. I know that they could be a little painful there, but I hope that it turns you into a better student, or it helped do that. As far as the final, these are the topics, and let me just go through each one of these and kind of explain in a little more detail what I'm looking for here. We never tested over Lagrange, but there were all these different types of Lagrange multiplier problems. I promise you I'm going to give you a function of 3 variables with 1 constraint. So you can focus your attention mostly on that. You're not going to have a 2-constraint problem. And I'm going to try and keep it pretty simple as far as the algebra that's going to be required for you to find your lambda and your x and your y and your z. I'm not going to have some crazy algebra that you've never seen before, all right? Just look at your homework problems for that section. 12.2, specifically, there was a section in the homework where you were given a double integral, like they wrote it out. Double integral, gave you limits of integration, they gave you the integrand. And they specifically told you to change the order of integration, which requires you to go and draw the region and then switch it from being a function of x to a function of y, or back the other way around. So it's in there. It's towards the end of the homework section, or homework problems for that one. For 12.3 through 12.7, triple integrals in cylindrical, polar, and spherical. There's a lot of information in those sections, but you can see from the problems that we did today, we had to do cylindrical coordinates, we had to do spherical coordinates. So that's the type of thing you need to know how to do. I'm not going to go back and pull like specific problems necessarily from those sections. You need to know when to employ those methods in an integral. 12.8, that was change of variables, and those problems could be kind of long. This is going to be kind of a plug and chug problem. I'm going to give you a transformation, and I'm going to ask you for the Jacobian determinant. That's it. Which means you need to know the Jacobian determinant. And what I'm allowing you to have on the test, I haven't told you yet, right? So let me get to the end. 13.2, line integrals along scalar functions and vector fields. So you need to know how to compute line integrals over scalar functions, but then you need to do it over vector fields, which is work, right? That's what work is. Most likely, those line integrals will not be on closed curves, right? Because then you might employ Green's theorem, or the fundamental, well, 13.3 is fundamental theorem of line integrals. You need to be able to find a potential function. Okay, so I'll give you a problem. I'll say, hey, find the line integral over this vector field, and you can do it easy way or hard way, right? Easy way is to find the potential function, plug in the 2 endpoints, be done, right? Green's theorem, I think that one's going to really stick out when you see it, because it'll be 2-dimensional, it'll be a closed curve, and you'll be asked to try and evaluate it, line integral. So you'd use Green's theorem. Green's theorem is in your packet of formulas, isn't it? That big packet of things that I handed you, I'm going to let you have that on the test. Okay, 13.7, surface integrals. There was a lot in this section. If I give you a picture of the surface, you need to be able to find parametric representations of the surfaces. Very similar to the handout that I gave you. Remember that handout? Okay. You need to be able to find the surface area. So I give you a surface, a scalar function, and you find its surface area. Or even if I give you the vector function. You need to be able to do flux. The last two, Stokes' theorem and Divergence Theorem. Stokes', you'll kind of know when to use that, because you're going to have a surface. You're going to be trying to do a surface integral, and there will be a curve going around it, or the other way around. There will be a curve going around a surface, and you decide which way you want to go with that. So that's the most recent information, right? That was the homework from last time, which hopefully you did, but I mean, no one had seen me do the cube problem yet, so. Divergence theorem, 13.9, that's today's stuff. So, what do y'all think? Y'all worried about it? How do you feel? A little bit? Yes.
Can we still make our own review sheets?
Yeah, this is what I'm going to let you do. I'm going to let you use one 8.5 by 11 sheet of paper, both sides. You may write steps, procedures, formulas, reminders, hieroglyphic shit that I don't understand, but you understand. I don't care what it is. You just cannot have any worked out problems. So if you're kind of like, well, I don't know if he'll let me have this, then don't put it on there. Because what I'll do is I'll walk around, and if there's something on there that gives you an unfair advantage over someone else, then I'll just take the whole thing away, and then you won't have it at all. So if there's any like uncertainty, don't walk in right before the exam, 3 minutes before the exam, be like, is this okay? Because I'm not going to do that for each of you, right? So if you're concerned about it, just send me a picture of it or something. I think it's straightforward, right? No worked out problems. You can have letters. You can do like weird letters and, you know what I'm saying? Code, some code, yeah. Phones, no phones on the test, right? Calculators are allowed. Don't go trying to program shit into your calculators. I know all about that stuff. So, all right. Normally, when I give a test, if the first thing a student does is picks up the calculator and starts pounding away on it, then there's a problem, right? Anything else? Any other questions? Test is on Wednesday, right? So you have a full week, plenty of time.
How many questions do you have?
I look at that right there. How many bullets are there? 4. There's 15 bullets there?
No, it's 12.3 to 12.7.
Oh yeah, but with 12.3 through 12.7, what I'm saying by putting them all in one bullet is that's kind of gonna be killed off as you do other problems in the test, right? Like you're gonna do cylindrical when you're doing a divergence problem possibly, right? So I don't know. How many bullets are there? 10? So it'll probably be about 40 problems. I don't know, 10 to 15? We'll see. I've looked at a couple of my old finals, and they all range around 10 to 15 problems. All right. I don't have anything else for you. Have fun studying for your other finals. Yep.
So you said no phones, but could we bring music devices?
Man, that's becoming a touchy issue nowadays. I personally don't have a problem with it. Here's the only thing, is that, when you go to a different school, like they're just not going to allow that, I think I'm giving you the formula sheet front and back. Let's let that be your comfort blanket, all right? Not the music. I understand how that kind of helps, but let's try and not have that. All right, so we'll say no music for the test. Okay. Y'all have a good one. Yeah. Do that, just run a big loop of the whole semester of my audio.
Hey, yo, you're giving me ideas.